Hello class, and welcome to today's algebra lesson, which is about the shapes of graphs. By the end of today's lesson, you will be able to determine if the graph of a function has a line of symmetry and where those lines are at, identify the extrema of functions and where those functions are increasing and decreasing, and then finally determine end behaviors of graphs. So we're going to start with the symmetry piece. Line symmetry means that each half of the graph matches the other side exactly. So think of it as the left side of the graph is an exact mirror image of the right side of the graph. So our first job is to decide if these functions have symmetry, and if they do, we need to identify it. If they don't, we need to explain that they do not have that. So, looking at this first function on the left, we have a straight line. My job is to try and put in a line somewhere along here vertically so that if I folded that graph in half, the two pieces would match up. Unfortunately for this one, there is no such line. So we would say that there is no line of symmetry, which you can abbreviate to LOS, because the graph cannot be cut in half. So when you are saying that it does not exist, you need to note that the graph cannot be cut in half. There is no line that makes that possible. If I come over here and look at my second example, right here down the very direct middle of my graph, if I put in that line right there and I was able to fold that graph in half, the two pieces would line up exactly. So in this case, yes, there is a line of symmetry, and that line of symmetry is located, if we look, it's at a vertical line, so that's going to be at an x value. All of these different x values are the same, of 1.5. 1.50, 1.51, 1.52. Down here it's 1.5, negative 0.5. So all of those x values line up to make that line of symmetry at x is equal to 1.5. Go ahead and try this one on your own. Once again, there is no line that can cut this function directly in half. We have a little dip at the bottom here and a little dip at the top there. There is no line then that can cut this in half. Our next piece is going to be to find lines of symmetry and interpret them within the context of a problem. So this particular graph shows the path of a golf ball after it is hit off the tee. So we are looking for the point where this graph gets cut in half, and it looks like it is about right here. Because I cannot see exactly, based on the labels here, we're counting by 25s. So because I cannot tell exactly where this graph is cut in half, I'm going to go ahead and make my best guess. So I'm going to say my line of symmetry is going to be at x is equal to, I'm going to put that at about 90. Again, we're counting by 25s, so 25, 50, 75. It looks like we're a little over halfway between 75 and 100, so I'm going to put that at 90. And then I need to interpret the meaning. So what this means is that the path of the ball, since I want to be specific about what I am talking about in the context of this problem, from the start, which would be 0 seconds, to 90 seconds, matches the path of the ball. So we have it matching, aka being symmetric. So matches the path of the ball from 90 seconds, so from that turning point now to the end of my graph, which is going to be at 180 seconds. So we have that perfect symmetry between the two pieces. Go ahead and try this one on your own. So our line of symmetry is that x is equal to 2. And within the context of this problem, that means the path of the water is the same between 0 and 2 seconds as it is between 2 and 4 seconds. We only go up to 4 here because our path is we want the part that actually matches. Next thing we're going to look at is when functions are increasing and decreasing. So the increasing is the part of the graph where it is trending up. The physical curve or line of the graph is moving in a positive direction. And on the flip side of that, the physical curve of the graph is going down when it is decreasing. Extrema is the general term for relative highs or lows within a graph. Specifically, the high points are called relative maxima. We call it relative because we are only looking at the points around it. There may be a higher point later in the graph, but this relative maximum is a point where a graph changes from increasing and flips back down to decreasing. On the flip side of that, the relative minimum is a low point on the graph, and it's where the graph goes from decreasing back up to increasing. So we're going to start by looking at these intervals of increasing and decreasing. So I'm going to start with this particular graph. As I start on the left of my graph, I am moving up. So that means that part of the graph is increasing until it comes to this point up top. So the increasing is on the left side of that top point, which means it's for the values that are less than, in this case, it's 2.5, because that's where my maximum, my changeover point occurs. So the graph is going up until it hits 2.5, at which case it starts to trend downwards, meaning that my decreasing part of the graph is going to occur after 2.5 or when x is greater than 2.5. Go ahead and try this one on your own. So in this case, I've got the increasing part happens after the change, so it is x is greater than 0, and the decreasing part happens on the first half of the graph, so x is less than 0. After I look at the trends of the graph, I want to be able to identify those extrema, or what is the relative maximum and minimum. So, as I'm looking at this graph, I've got it traveling as an increasing path all the way until it hits point B. So that means that point B is a relative maximum. It is the highest point at which there is a turn from increasing back down to decreasing. Then, as I keep going, I'm going to hit a low point at point C, which is a relative minimum. That is a low point compared to anything else around it on the graph, and it is a point where I go from decreasing back up to increasing. Point A and point D are not maximums or minimums because they are not at a point where it is changing the direction of the graph. So in this case, point A and point D are nothing. Point B is our maximum, and point C is our minimum. Go ahead and try this one on your own. In this case, we have two relative minimums, point B and point D. Both occur when we are going from decreasing back up to increasing. And point C is a relative maximum going from increasing down to decreasing. We also want to be able to identify these extreme points within the context of a word problem. So the graph shows the earning of a comic book store compared to the selling price of comics. So our first job is to identify the extreme value, which in this case is obviously going to be point D. And point D in this case is a relative maximum. It is a high point within our graph. Now I need to decide what that means within the context of my problem. What it means in this case is that point D represents the highest profits, so the greatest earnings that we could have, the greatest earnings that we can have based on the selling prices of the comics. So what it's saying is basically that if the comic store sells its comic books for $4 each, it's going to make a maximum amount of profits. Go ahead and find and interpret this extreme value on your own. In this case, point A is once again a relative maximum, and that means it is the tallest height of the plane during the particular stunt that they are flying. The last thing we're going to look at in this lesson is called end behavior. This is the values of the function at the positive or negative extremes in the domain. AKA, it's looking for, as those arrows point out the end of the graph, what are the values actually doing? So if I am looking at this particular function right here, it is a linear function. So the first thing I want to do is say, all right, as we are going to the left, so as the x values are decreasing, what is the trend of my y values? So as x decreases, as we move to the left, our y values are also decreasing in this case. So as it moves to the left, the end behavior going to the left is that your values are going to decrease. As I'm moving to the right, so as my end values increase, this particular line has the y values also increasing. So moving to the right, your y values continue to go up. Go ahead and try this one on your own. In this case, as you move to the left, so as your x decreases, your y values are actually going up. And as you move to the right, the increase in x means that you have a decrease in y. We also want to be able to do this for nonlinear functions. So once again, I'm going to start by looking at as I move to the left. So as the x values decrease, I'm looking at the left side of my graph and it is still trending down. So as x decreases, y also decreases for this graph. And when I flip over to look at the right side, the right end behavior, so as our x values are increasing, and we follow that arrow on the right side of the graph, my y values are also increasing. Go ahead and try this one on your own. In this case, as I move to the left, that left arrow says that as my x's are decreasing, my y's are increasing. When I flip over to the right side and my y's are increasing, my x's are increasing, my y's also are increasing. If you have questions about this or anything else from the lesson, please feel free to reach out and let me know.